Chapter 2, Matrix Algebra. So 2.1 talks about matrix operations. So what operations we can apply on matrices? That A, B, and M by N matrix. Then a general way of writing A is given here. Remember, A is, we have seen what a matrix is. You have an idea. It's a arrangement of numbers basically. So an array of numbers we say. Here are numbers arranged in order. So we have the first entry of the first row and first column, because remember m by n is the size of the matrix, where m is number of rows and n is number of columns. So always remember that when we talk about the size of a matrix, we always have to have the number of rows first and then number of columns. So this matrix has n rows, m rows, because you see here 1 1, 2 1, 3 1, so on, and then we have m1. So because the first number or first digit is the rows and the second is the column. So they are all in first column and these are all in the second column. So m1 2 2 2 3 2 and so on, m2, and there are n columns, so that's why we end at 1n. Now the entry in the ith row and jth column is denoted by a sub ij. That's what we have here. And a short way of writing the matrix A is equal to, the square brackets, and inside we write aij. Now note that each column of A is a vector in Rm, because there are m entries in each column. If we denote the columns of A by vectors A1, A2, A3 and so on, then A can be written as like this. We have seen this before in chapter 1. The diagonal entries of A are A11, A22 and so on. It can be a square matrix or it may not be a square matrix, so we don't know what will be the last entry. Now the diagonal entries of A are these. So a diagonal matrix is a square matrix of size n by n or m by m, in which all non-diagonal entries are 0. Now note here, we have the restriction on the entries which are not on the diagonal. We must have those equal to 0. Does it mean that we should have no 0 on the diagonal? That is not correct. We can have some zeros, but at least one entry on the diagonal must be not 0. So for example, here we have a diagonal matrix. Why is it diagonal? Because the diagonal has entries. So A11 here, this is 1 2 3 4 5 5 by 5 matrix. A11 is 1, A22 is -4, A33 is 0, this one, A44 is 3, and then A55 is again 0. So we can have some 0 entries, but not all of them should be 0, because then it would be a 0 matrix. So an identity matrix is a diagonal matrix, so it means it's a square matrix with all the diagonal entries equal to 1. An n by n identity matrix is denoted by I sub n or simply I. Some of these identity matrices are written here. So this is of size 2 by 2, this is 3 by 3, and this is 5 by 5, and you should be able to write the any size identity matrix. Now an n by n matrix whose entries are all 0 is called a zero matrix. The size of a zero matrix is usually clear from the context. Now two matrices are equal. So remember we learned when are two vectors equal. Similarly, we can talk about matrices, equality of matrices. So we said that two matrices are equal if they have the same size. That is the first thing. If they have a same size and their corresponding entries are same or corresponding entries are equal. If A and B are m by n matrices, then the sum A plus B is obtained by adding the corresponding entries of both. For example, if A is our 2 by 3 matrix here and B is a 2 by 3 matrix given here, then if I want to find A plus B, then it will be A11 plus B11, A12 plus B12, and so on. So corresponding entries get added. Now, what about scalar multiplication? If A is a matrix and R is a scalar, then R times A will be equal to R A11. So what happens? Each entry of the matrix is multiplied by the scalar. So you can see here. Let's look at a theorem. So this says let A, B, and C be matrices of the same size, and let R and S be scalars. Then A plus B is equal to B plus A. Now, if you recall, these properties, these are kind of properties of matrix addition and scalar multiplication, and they look very similar to the properties of vectors that you saw in chapter 1. So A plus B is equal to B plus A means the matrices, addition of matrices obeys the commutative law, or the matrices are commutative under addition. Second, B is A plus B plus C is equal to A plus B plus C. Means if you are adding these two matrices first and then you add C, you will get the same result if you had added B and C first and then added A in the result. And what is this property? This is the associative property. C is saying A plus 0. This is not the number 0, this is the matrix 0. So the A matrix plus the 0 matrix gives you back the A matrix. Again, this is comparable to the numbers. 2 plus 0 is 2. That's just for the numbers. Now here we have that property for the matrices, and this is called the identity property. Additive identity property. So 0 is called the additive identity. Then B says R times A plus B is equal to RA plus RB. So R is a scalar, and if you multiply the sum of two matrices with a scalar, you will get the same answer as if you first multiplied each matrix with the scalar and then added the result. This is kind of distributive property, a distribution law. E is also a distributive law, but here now we have R plus S. We have two scalars being added and being multiplied with A. So it will be the same as if we multiply A separately by each scalar and then added them. Then we have R times SA is equal to R into SA. So if you have two scalars and you are multiplying your matrix any name matrix, you multiply first by one scalar and then you multiply the result by another scalar. It's this, you get the same thing as if you multiply the scalars together and then multiply with the matrix. So now we talk about matrix multiplication. Now the addition was easy. You just add the corresponding entries. What about the matrix multiplication? So the rule is that if A is an M by P matrix, so M rows and P columns, and B is a P by N matrix, so P rows and N columns. So note here these two are the same. Then AB is an M by N matrix. So where am I getting this M and N? From this and this. So outer numbers. The M by N matrix AB will have the size M by N. And how do we multiply? A, we can write A like this. We can write B like that. Then A times B will be the same as the matrix A multiplied by the vector B1. Then second column of the AB matrix will be the matrix A multiplied by the column of B2, second column of B, and so on. Now, it might look a little complicated or complex, but when we do examples, you should be able to see that. Now, note if we have this situation that we have a matrix where we call from our chapter 1, and X is a column vector. Basically, this is also a matrix, just a column, one column. So when you multiply A with the X, so the AX matrix, which will be actually a vector, how do you multiply it? X1 A1 vector plus X2 A2 vector plus so on. Last one will be XP AP vector. That's why this number here and this number here should match. Here it is the number of columns, here it is the number of rows. Okay, so now we talk about the properties of matrix multiplication, and we have a theorem saying let A be an M by N matrix and let B and C have sizes for which the indicated sums and products are defined. So remember, in order to add matrices, they should have the same size. In order to multiply matrices, the number of columns of the first matrix, when I say first means the one written on the left, must be equal to the number of rows of the second matrix, means the matrix which is written on the right. So now note here, this the first property is the associative property. So in the past we saw the properties of matrix addition or vector addition. We saw the first property was commutative property, but here we do not have a commutative property, and you will see when we do examples that often and two matrices A and B, the AB will not be equal to BA. This is a very general thing in matrices. So property number 1 is associative property of multiplication of matrices. This B1 is the distributive property, multiplication over addition. So this says A times B plus C is equal to AB plus AC. Now we have to be very careful about the order of the product. In numbers, remember that we don't care much how we write it, but in matrices we have to be very careful. So here we have now B plus C. Now look here, A is being multiplied on the right of B plus C. In B, part B, A was to the left of B plus C. So when you distribute, it must remain on the left of the two matrices. But when A is on the right of two matrices, when you multiply or distribute, A should remain on the right. With numbers, we don't care. If we have 2 into x plus 3, we can, or if we have x plus 3 into 2, you get the same answer. But with multiplication of matrices, that is not true. Next is that if you have a scalar being multiplied by AB, then we could have the situation that the scalar was with A, and you multiply the A matrix with the scalar and then multiply the result with B, or you can have the scalar multiplied to the B matrix and then multiply with A. Now, identity matrix into the A matrix. So in order for identity, now remember A is order m by n. So when I write the identity matrix, which identity matrix we can use? If we are on the left, it should be the m by m, and if we put the identity on the right, it should be n by n. Why? Because remember A is of order m by n. So the second number here should be the same as the first number in the order of I, and then same situation on the other one. So warnings, in general, AB is not equal to BA. I already mentioned that. Second one is that the cancellation laws do not hold for matrix multiplication. That is, if AB is equal to AC, then it is not true that B is equal to C. Now, if you recall with numbers or in algebra, if I have x times y equals 3x, we can divide by x and or cancel x and say y is equal to 3. But in matrices, you cannot do that. Also, if you recall, there is a zero product property for matrices, for numbers, which says if A times B is 0, then A is 0 or B is 0. This must happen. One of them must be 0, at least one of them. Both can be 0, but at least one of them is 0. But with matrices, if you get a product to be 0 matrix, then you cannot say that A is the 0 matrix or B is the 0 matrix. So the zero product property does not hold in matrices. The powers of matrices or matrix. So if A is an n by n matrix, now in order to multiply the matrix by itself, if it is of order of size m by n, as we saw before, so if we have the matrix A, which is of size m by n, I cannot multiply it with A. I cannot get the product A times A because this will be of size m by n. So these two numbers don't match. We cannot have the product. So in order for to find powers of a matrix, the matrix must be a square matrix. So we are saying if A is an n by n matrix, then A square is the same thing as A times A. A cube will be A times A times A, and so on. So in order to find these products, you can find A times A. Then to find A to the third, you can say this is A times A square. So you already have this. I multiply with A, and so on. Now note here, in this case, you can multiply on either side. So A cube can also be thought of as A square times A. Okay, the last thing here, I think, so this is transpose of a matrix. Transpose of a matrix. Given an m by n matrix A, the transpose of A is denoted by A transpose and is an m by n matrix obtained by interchanging rows and columns of A. So we have a theorem for the transpose. So let A and B be matrices whose sizes are appropriate for the following sums and products again. Then A transpose transpose. So transpose of A gives you back A. A plus B whole transpose is the same as A transpose plus B transpose, which is the same as, if you recall, B plus A transpose. Because this can be written as B transpose plus A transpose. So this also satisfies the commutative property. R times A whole transpose. So if you have a matrix multiplied by a scalar and you want to take the transpose of that it will be the same as if you first took the transpose of A and then multiplied by the scalar. The product, transpose of the product. Now note here, it doesn't come out as A transpose times B transpose, as you would expect, but it gets reversed. So the transpose of a product is the product of the transpose of each matrix, but in the reverse order. Okay, so this is the end of section 2.1, and let's look at some example here. So this is mostly computation. I will do a few and then you should be able to do the rest of them, and then I will show the work in the next video. So let's look at this first one, 3a minus 2d. So you can start over here. 3a minus 2d will means I multiply the matrix A by 3. So that will give me 12 minus 3, 9, 6, minus 9, and then 3. That is 3a minus 2d. So 2d will be 4, 4, 4 in the first row, minus 6, minus 2, and then 2. And now what I do, because this is a negative sign, we can think of it in two ways. We can have a plus sign here and then multiply each of the entry by -1, or we can just subtract the corresponding entries. So you read it as 12 minus 1, -3 minus 4, 9 minus 4, then second row 6 minus -6, so it becomes 6 plus 6, -9 minus -2, so it becomes -9 plus 2, so we get -7, and then 3 minus 2, so we get 1. So that is how you should show the work of this. Next is A plus B. So can we add A plus B? No, we cannot. So A plus B is not possible because the sizes are different. Size of the two is not the same. So next is asking us to do AB product. I will let you try these and then I'll come back and show you how to do these in next video.